Good morning to you all. Um, Today's lesson is, as you can see, 4.7 optimization problems. But and the last group of problems are what? Maybe a half hour, 20 minutes to a half hour each. So while I can't maybe go through a whole problem, are there any, I don't know, any problems that came up? Any questions you would like to ask? Anything you'd like to talk about from 4.6? All right, let's get going on 4.7 then. So optimization, this is always one of my favorites, and it's one of the unique things that calculus allows you to do. We're going to start off with a classical calculus problem, one that always comes up and is kind of famous, for, at least from what I've seen. It's in every book, every calc book. And it goes like this. And I think this is from this, let's see, I don't have a book here. Let me just take a look. So from 4.7. Yeah, here's example 1. Again, it's the box problem. I'm just trying to look. The number 2, is that from the assignment? Yep. So what I'm doing, this number 2 we're working on, that's basically the problem. Okay. So numerical, graphical, and analytic analysis. An open box of maximum volume is to be made from a square piece of material, as you've seen shown on the left, from which you're going to make a box. So what you got to do is cut out the 4 corners and then fold up the sides to give you a box, as you see in the drawing at the right. And here's the big thing. All right, so the material is 24 inches by 24 inches to start off with. And what you've got to do is figure out how big of a cutout, how big of an X do you need to cut out of the corners so that when you fold it up, you will get a volume of maximum size. You know, I mean, for example, if you made the cutout 12 inches, what would happen? 12 inches out of each corner and you wouldn't have any bottom left. So that's not going to work. If you take out just a little, then the box is going to be just a slight, very small height. And that may not give you a very big volume. So the question is, what's the ideal cutout to give you maximum volume? And you notice the word maximum is a good match for what we've learned this year. So I'm going to skip the A and the B, and we're going to go right to part C, down at the bottom there. Use calculus to find the critical number of the function and find the maximum value. Okay? So that's the problem, and we're going to work it out right now. Okay, so let's figure out what we got here. We're going to make a volume formula because that's basically what it is we're trying to maximize. And then for volume of a box, it's going to be what? Length times width times height. Okay, what are the length and the width? And if you look to the picture over there, you should be able to see that when you chop out an X out of each corner, you have to take 2X off of the width. And so whatever X is, the width will be 24 minus 2X. And the length will be 24 minus 2X. And the height will be X. So X times 24 minus 2X times 24 minus 2x. Does that make sense to everybody? So you've got your three-dimensional object, length times width times height. Okay, we probably need to do some multiplication here. So, all right, x times, all right, 24 times 24. Yeah, force. So 576. Then 24 minus 2x, so that's negative 48x. And then negative 2x times 24 is negative 48x. And negative 2x times negative 2x is positive 4x squared. And then when we multiply the x out, and then I'm going to put the highest power first, you would get 4x cubed minus 96x squared plus 576x. That would be our volume. All right. Now, the whole idea is to maximize it, so we're going to want to take the derivative. So v prime 12x squared minus 192x plus 576. Okay. So now, how does one we've got the derivative. How do we get a maximum out of this? We would set the derivative equal to 0. Okay, so can we factor this at all? Well, it looks like we can take, yeah, we could definitely take out a 2. Can we take, let's see. 12 won't go into everything, will it? No, because 12 times 4 is 48. It might. 12 go in there? 576 divided by 12. 48, yep. So, and 192 divided by 12. Yeah, so we can take a 12 out of there. So 0 equals 12 times x squared. And now I forgot, what's 192 divided by x? 192 divided by 12, 16. And then 576 divided by 12, 48. Okay. Can we factor that even further? Well, let's see. 48. What? 12 times 4? And if they're both negative, that's going to work, isn't it? So we get 0 equals 12 times x minus 12, x minus 4. Let's just see, did I factor that right? So the inside we get negative 12x, negative 4x. Yep, there we go. So we can solve this. When might this equal 0? When x equals 12 and when x equals 4. Now, go back to the practicalness of the problem. Remember, x is the cutout. If we cut out 12, what kind of a box would we have left? If you put an x, if you cut 12 out of each corner, the bottom would be gone. 12 plus 12 is 24. Nope, no bottom at all. So that's out. So even though that turns out to be calculated correctly, that doesn't really come up with a solution that makes any sense. So how about 4? Sure. If you cut out 4 out of the bottom, that's 8 off. The bottom would be 16. So this right here is the best cutout we can do. And then let's figure out what the volume is at that stage. Okay, so volume at 4, and let's just do it. It's 4. I'm just going way up to the top here. 4 times 24 minus 8 is 16. 24 minus 8 is 16. So 16 times 16 is 256. And 256 times 4 is what, 1024? Let me just see if I did that right. 16 times 16 times 4. Yep. So the best volume you're going to get out of that box is 1,024 cubic inches. And what's the best cutout? If you take 4 inches, make these little, so right here is where, you would take a 4-inch by 4-inch square out. That'll give you the maximum. Any questions? So that is kind of a classic problem, and I don't know, one of my favorites. So of course you could change the facts. It might not be a 24-inch box. It might be, 80-inch box or whatever. I mean 80-inch square. But the concept would be the same. Okay. All right, let's take a look. So now I'm jumping right to the assignment, and we're going to take a look at problems that you might not think of as this type, but they are. Yeah, get this box in the right place. Okay. So, and we're going to work on the evens, and obviously I'm going to give you some odds. But so number 4 says, and you got to kind of read these by looking at the directions at the top. It says find 2 positive numbers that satisfy the given requirements. In number 4, the 2 numbers have a product of a 185, and when you add them up, you get a minimum. So instead of maximizing, this time we're minimizing. Same deal though, right? When you have a minimum, the first derivative will be set equal to 0. So it's the same concept again. So if 2 numbers have a product of 185, how can we write that? So, well, all right, let's call the 2 numbers x and y. Okay, so x times y equals 185. And what you can do then is come up with this new name for y, which is 185 over x. So really now, what are your 2 numbers? They're x and 185 over x. Do you follow? So we started off, we don't really want to use 2 different variables, x and y. But to get going, this is what you would do. X times y equals 185, and then we'll come up with an x way of saying y. So in effect, what we have just said, let me just mark this down, is our 2 numbers are x and 185 over x. So now that we've redefined that, now go to the problem, and the problem says their sum is a minimum. Their sum is a minimum, so we've got to add them up. So here I add them up. X plus 185 over x, that's our function, the sum of those 2 numbers. And you can see in green, I'm already getting ready to combine those with a common denominator. So the left number, I am multiplying by x over x. All right, so then we can add them. And when you add them, you get x squared plus 185 all over x. Okay, so there's our sum. So now we need to minimize that. All right? So in preparation for taking a derivative, I'm going to rewrite 185 over x is 185 x to the negative 1. Now take your derivative. Derivative of x is 1. Derivative of 185 x to the negative 1, power rule, negative 185 x to the, lower the power by 1, negative 2. And now what do? Once you found the derivative, you set the derivative equal to 0. Okay, so that's the next step. And then I rewrote negative 185 x to the negative 2. I went back to getting rid of negative exponents. All right, so we solved that. We should be able to find where it's a minimum. And what I did is I added 185 over x squared to both sides. Multiply both sides by x squared. Take square roots. I make the comment that, you know, there's really two of them, right? There's 2 square roots of 185, plus and minus. So plus and minus about 13.6. Let's take a look at that one and see what that looks like graphically. Let's see, what was our function? Right up here, x plus 185 over x. Desmos. X plus 185 over x. Okay, gotta find it. There it is. And so now we're trying to find what? The minimum. Now, the left side of the graph is out of play because do you remember the directions were find two positive numbers that will make this happen? So we're not going to be over here on this left branch. We're going to be over here on this one. And the minimum is the low point here, which is somewhere in there. And so what do we get for an answer? 13.6. So if you look back on here, yeah, there we are, 13.601. So our answer does make sense. And here's a case where you have to remember the practical, the practical points of the problem. Let me just go back and show you the directions on this section are find 2 positive numbers that satisfy the given rate. Okay, so, all right. So any questions on that? All right, let's go to another one. We'll go to number 6. The second number is the reciprocal of the first number, and the sum is a minimum. The second number is the reciprocal of the first number, and the sum is a minimum. Okay, so that shouldn't be too hard. Reciprocal, so if one of them is x, the other one's 1 over x. Okay. And now we've got the 2 numbers are x and 1 over x. All right. And their sum is a minimum. So we add them up, x plus 1 over x. Getting ready to do what? A derivative. I rewrote that as x plus x to the negative 1 power. Okay. And then we take the derivative. The derivative of x is 1. The derivative of this is negative 1 x to the negative 2, which puts it in this form. And then you set it equal to 0. A little bit of algebra would tell us if we add 1 over x squared to both sides, and then we multiply both sides by x squared. So there's 2 answers here, 1 and negative 1, but -1 violates the principles of the problem. The problem said two positive numbers. So we just got 1. Well, if x is 1, then what's its reciprocal? 1. So over here, I just kind of said, all right, those are my two numbers. So you see how we actually get two answers here, 1 and -1, and we have to throw out the -1 because of the constraints of the problem. All right. Anybody have any questions here? All right, let's go to, oh, here we're going to do an odd. Okay, number 7. So these get a little bit more challenging as we go on. So we've got these two positive numbers. The sum of the first number and twice the second number is 108. And the product is a maximum. Okay, so there's a couple little extra challenges here. So if we just begin temporarily, call the two numbers x and y, then the sum of the first and 2 times the second is 108, would give us this equation right here. Now we're going to solve for y and get an x answer for it so that we can proceed. And that's what I do. Let's subtract x from both sides, and that gives us 2y equals -x plus 108, and then divide both sides by 2. So there's my second number, -1/2 x plus 54. So just to get some perspective here, over here, these are now my two numbers. So they started off being x and y, and now I found out by using the constraints of the problem that another name for y is -1/2 x plus 54. So here now is where we're going to proceed. X is the first number, -1/2 x plus 54 is the second number. All right. So now the book says their product is a maximum. So the first number times the second number equals our function. And to maximize it, we will once again find the derivative, and then we'll set the derivative equal to 0. So here's my derivative. Well, I first multiplied x times, I first multiplied x times this quantity, -1/2 x plus 54. Now we're ready to do the derivative. Okay, so derivative of -1/2 x squared would be -x, right? Because 2 times -1/2 is -1, and then lower the power by 1, x to the first, and then so there's my derivative. Set derivative equal to 0. That's a real rough one to solve for x. Not really. 54. Well, where did I get the 27 from? Well, remember, we've got the name for the second one. So we found x. What's -1/2 x plus 54? Well, -1/2 of 54 is 27. -27 plus 54 is 27. So what are the two numbers? 54 and 27. Everybody on board with all those steps? All right. Number 8. The sum, so again, we're still on this two. We got to remember here the goal is find two positive numbers that satisfy the given requirements. All right. So number 8, the sum of the first number squared and the second number is 54, and their product is a maximum. So again, we'll start off with x and y. And when you add the square of the first number, x squared, plus the second number, y, you get 54. So let's get rid of the y now. Let's solve for y. Subtract x squared from, so there's my, so now I've got two x ways of saying the number. So here are now my two numbers, x and 54 minus x. All right, so now that I have my two numbers, what does the book say? The product is a maximum. Product. So I take the two numbers and I multiply them. X times 54 minus x squared. Multiply that out, 54x minus x cubed. Take the derivative, 54 minus 3x squared. Set the derivative equal to 0. And then just do the algebra. Add 3x squared to both sides. Divide by 3. Take both square roots. Well, I say take both square roots, but if we had negative 3 times the square root of 2, it's not a positive number anymore. So just so you know, I know that, but I ignored that because I knew we were going for. So now we know x is this number right here, 3 times the square root of 2. So if you look back up here in the left margin, we've got that. How do we get this 36? Well, we just square this. You get the 54 minus x squared. This squared is what? 2 times 9 or 18. And 54 minus 18 is 36. So what are the two numbers? 3 times the square root of 2 is one of them. And the other one is 36. Comments? Questions? Welcome, Jenna. I know you've been here a long time. I just didn't see you on the list. All right, let's go to another. Not hearing any questions. Let's go to number 9. So now we have a new set of directions here. This time it says in 9 and 10, and this is, notice 9 is an odd. In number 9 and 10, find the length and width of a rectangle that has a given perimeter and a maximum area. So the perimeter is given to be 80 meters in number 9, and you're supposed to figure out a way so that the area is a maximum. So we're jumping from perimeter to area. Okay. So what's the perimeter of a rectangle? 2 lengths plus 2 widths equals, your perimeter. So there's your function. And we were told that the perimeter is 80. So instead of just f of x equals that, we have 80 equals 2L plus 2W. But again, now we've got two letters, L and W. So we should be able to, what, get rid of one of them, solve for W. So I first subtracted 2L from both sides, divided both sides by 2. So now we're finally at the point where we've got our two numbers named, and there they are, L and 40 minus L. Now, if those were the two sides of a rectangle, can you find the maximum area? So obviously the area, we've got to multiply them. So there we go. Our function now is multiply the length times the width. Multiply that out, and we get 40L minus L squared. Now, guess what? No big shock. We're going to take the derivative, which is 40 minus 2L. And then we're going to set that equal to 0. And we're going to solve for L. So the length needs to be 20 meters. I didn't put the label down there. That should be a meters down there. 20 meters. So if the length is 20, what's the width? Yeah, it turns out to be also 20, right? And we have found, so this is not too surprising. A lot of times when you want to find a maximum or a minimum in a rectangle, you will end up at a square. Don't assume it, but that's often how these max-min problems work out. Any questions? You know, obviously the calculus here has been very simple. It's more the setup of the problems where students sometimes get hung up. So pay particular attention to, I'm trying to describe these in words to you so that you get an idea of how I'm planning the problem out. All right, let's go to another. I guess we're going to do number 10 now. So number 10, find the length and width of a rectangle that has a given perimeter. This time we only have P units. Okay, so we have an extra little complexity here. Instead of having a number that is the perimeter, we have a constant, P. All right, so yeah, so I mean, all right, I sketched out a rectangle with width and length, and we still know that 2L plus 2W, instead of equaling 80 this time, it equals P, all right? And P is just a constant, so P is not a problem. I know it doesn't look right, but it's fine. So now we still want to do what we did before. We don't want W and L. So what we do is we solve for W. 2L plus 2W equals P. Subtract 2L from both sides, divide both sides by 2, and I've got this new name for the width. So I didn't do it this time, but what are my two sides? I've got the length, and I've got this. This is my width. So length times width, that's my function. And that's what I want to maximize. All right. So sometimes, like I said, the hang up for students is getting the problem set up. Well, we got the problem ready now. So now we can go ahead and multiply this thing out. So, I mean, P over 2, if P is a constant, P over 2 is a constant. You don't have to do anything there. So, sorry. Excuse me. Let me just get my formula here. Yeah, so I use the product rule. Okay. So, yeah, so when you multiply this out, you get L times P over 2. L, I just called it L to the first power. And L times minus L is negative L squared. So now when you take the derivative, how do you take the derivative of P over 2 times L? It's just that constant, P over 2. And how do you take the derivative of minus L squared minus 2L? Okay. Set it equal to 0. And you're okay with P, just solve for L. So I added 2L to both sides. I divided both sides by 2, and I got P over 4. So what does that tell you? I mean, if the length is the perimeter divided by 4, if the length is 1/4 of the way around the square, doesn't that tell you it needs to be a square? So here we are back to a square again. Okay? So P over 4 is exactly the length you need. And of course, if that's the length, the width has to be P over 4 too. And if you just come back here and you went back into W here, and if you substitute in P over 4, you would wind up, I mean, if you plug in a length of P over 4 right here, you will wind up with the width being P over 4. Here, let's just do it real quick. Let me change colors so you can see what I'm doing here a little bit better. Okay, so W equals P over 2 minus P over 4. P over 4 is what we found down here. W, what happens when you take 1/4 of P away from 1/2 of P? You get 1/4 of P, and you can see both the length and the width are the same. In other words, we came up with a square. So a little more abstract there, but you don't have to have a number to do a problem. All right. I mean, you can have a constant like P or that and still solve your problem. Questions? Take a little bit of a time out here. I want to jam this stuff down your throat. Let's take a look at number 12. Minimum perimeter. In numbers 11 and 12, find the length and the width of a rectangle that has the given area and minimum perimeter. So this time we're given, before we were given a perimeter and then we were supposed to find the maximum area. Now we're given the area and you're supposed to find the minimum perimeter. Okay. So this time, and here we go with a constant again, we are given an area of A square centimeters. Okay. So width, length, and all I know this time is A is the answer to the area. So width times length equals area. And again, we don't want to have, we want to get rid of the W, so we at least only have one letter to deal with here. So if we solve for W, we get A over L. So basically, if you look over here, these now, I mean, we started off with width and length, but we've gotten it down to just this constant A and one variable, L. All right, now what are we supposed to do? Minimize the perimeter. How do you find the perimeter when you know the width? Oh, that's add 2 widths to 2 lengths. Yep. So here we go. 2 widths, 2 times, and there it is, A over L, plus 2 lengths, 2L, and that's our function. And now we need to minimize that. So once again, we will find the derivative. So I rewrote 2A over L as 2A L to the negative 1. Again, A is a constant. So we don't have to, I mean, we have to treat it as a constant. Now let's take the derivative. So derivative, negative 2A, reduce the power on L by 1, plus 2, and that would be the derivative. Set the derivative equal to 0. I rewrote the negative 2AL to the negative 2 as negative 2A over L squared. Subtract 2 from both sides. Multiply both sides by L squared, getting rid of the denominator. And get rid of the -2 on the right. Solve for L. Yep. So I came up with the length being, excuse me, the positive square root of A. Why only the positive square root? Because a rectangle can't be a negative length. So here's a case where the practical conditions of the problem, not because the book said give me 2 positive numbers, but because we're dealing with a rectangle and rectangles can't be negative. So, so how did I get, all right, so I can see how I got L equals the square root of A. Where did I get W from? Well, you could just come back up here to this point. And if you put a square root of A here, let's just write that out. So A over L equals, I'm sorry, let me do that again. So A over the square root of A, I substituted square root of A in for L, equals W. So what's A over the square root of A? So that's like A over A to the 1/2 power, and that equals A to the 1/2 power, right? Subtract exponents, 1 minus 1/2 is 1/2, and that means the square root of A. So both the length and the width, and sure enough, we're back at a square again, aren't we? Both the length and the width. So don't, whatever you do, don't assume this idea of a square, but you'll find out that in Max's, so in other words, a square is a very efficient way to make a rectangle. Okay. Any questions? Well, let's take a look at 21, number 21. Now we're at a real challenging problem here, okay? So I don't have the problem, so let's take a look in the book. Number 21. Yeah, so let me grab that. I'm sorry I didn't have that ready. Copy. Okay, so there's the way the problem is in the book. A Norman window, evidently that's the name for that window. A very beautiful window. It's got this semicircular top. And you can, for all practical purposes, kind of forget about the fact that there's a seam here. Okay. It says, find the dimensions of a Norman window of maximum area when the total perimeter is 16 feet. So the perimeter is given to be 16 feet. Okay, and we want to maximize the area. So we have, the biggest possible window. Okay. Now it makes it a challenge because to find the perimeter, it's kind of it's a little different because we have, we've got a semicircle added to a rectangle and all of that. So let's find the perimeter. And we know it's 16 feet. So I think you will agree that there's going to be 2 y lengths in this. So when you find the perimeter, go all the way around. And again, you don't have to worry about this cross piece. We're going to have 2 y lengths, one over here, one over here. So that's why I have 2y. Plus the bottom, x, plus the semicircular top. So what is that? Isn't that half a circumference? And what's the formula for circumference? Pi times diameter. But that's for a full circle, so we have to cut that in half. So pi times the radius. And that's what I did here. Pi times, and the radius is 1/2 of this x guy in the bottom. So basically, this is my perimeter formula right here. All right. We have too many letters. So what we can do is solve for y and get rid of the y. So 2y, and then I subtracted everything else from the right. I subtracted the x, and I subtracted the pi over 2x. And I got it down to, that's another name for y. So there is the name for my height. I'll call it that, the y. And x, well, that's itself. All right. So now the whole idea is, all right, what's the area of this thing? So we switch over. Well, we've got the area of the square plus the area of the semicircle. So I took, what's the area of the square? X times y. X times this expression for y. And for the semicircle, it's what? Area of a circle, pi times r squared. But I only have half a circle, so it's 1/2 pi r squared. So the radius is what? X over 2. No, x over 2 squared. Let's see. Let me just work this out on the side here. I guess that's what I did up in the corner. So pi, yeah. So if you look up here, way up here in the top, you can see it there. See my cursor up there? Pi times the radius squared, divided by 2 because we have a semicircle. Well, when you square pi over 2, you get, when you square x over 2, you get x squared over 4. And then when you put this all together over 2, you get pi x squared over 8. All right. So add up the semicircle and the square, and you've got the area of the Norman window. So now we start multiplying things out. Multiply out this x part, x times 8, you know. So when you multiply that out, you get that. Yeah, I don't know if I had to do this, but you notice I had 2 terms that were x squared terms, so I factored out the x squared out of those 2 in this term right here. And now I took the derivative because the whole idea is maximize the area. So we've got the area, now maximize it. So do you see now why I factored that out? Because when you take a derivative, you know, you want to have, it's nice to just have one, you know, that x squared term right there, and you can, anyway. The derivative of 8x is 8. The derivative of this is power rule, 2 times that quantity, -2, keep the coefficient, reduce the power by 1. Power rule, 2 times pi over 8 is pi over 4, reduce the power by 1. Set derivative equal to 0. So anyway, after you do all of that, you wind up with this for x. And it turns out that the ideal x is 4.48 feet. So remember, the whole constraint was the perimeter has to be 16 feet. So when the perimeter is 16 feet, you want to maximize the area, set up this bottom dimension as 4.48 feet. Excuse me. Problem solved. Doing too much talking. So anyway, we got through a bunch of examples today. I hope that helps. This is really I don't know, this isn't so much a difficult calculus because the derivatives weren't that hard, but setup of the problem and maybe a little bit of an algebra challenge. Exercises. So what do we got here? 3, 5, 1, 2, 3, 5, 9, 11, 20, 23C, 33. So we got 9 problems for you to work on. You guys have been really quiet. Any questions? Any comments? You want to say anything to your classmates? Thank you. Hi to you too, testing. That's so funny the way your identity is defined. Test space ing. Okay, I will say goodbye and I will see you on Friday. I'm sorry, I will see you tomorrow on Wednesday. Thank you.